So next up is the cross product. The cross product is sometimes called the vector product because in this case the result is a vector. Compared to the dot product, which we ended up with a scalar, the cross product gives us a particular vector that is perpendicular to each of two given vectors. So let's go through an example using the dot product to help us think about the cross product. So example 1, given vectors A equals -1, 4, and 7, and B equals 2, 3, 5, determine n such that n is perpendicular to both A and B. So recall that last time, if n is perpendicular to both A and B, then A dot n and B dot n must equal 0. So first, let's identify vector n. So let n equal x, y, and z. Then we know that A dot n is equal to 0. So that tells us that we have -1, 4, and 7 dotted with x, y, z is equal to 0. So this gives us -x plus 4y plus 7z equals 0. Let's do the same thing for vector b. So b dot n also equals 0. If we dot those two vectors, we end up with 2x plus 3y plus 5z equals 0. And I'm going to call these equation 1 and equation 2. So remember, we have two equations, but we have three unknowns. Last time we restricted a variable and then solved for the remaining two. This time we're not going to restrict a variable. Instead, we're going to express z in terms of x, and then we're going to express y in terms of x. So let's look at how to do that. So first off, to express z in terms of x, that means we need to eliminate y, so there's no y in our equation. And to eliminate y from equation 1 and 2, I'm going to multiply equation 1 by 3 and 2 by 4. So what I end up with is the following. When I subtract these two equations, I'm left with -11x plus z is equal to 0. And then if I isolate for z, I end up with z equals 11x. So there is z in terms of x. Let's do the same thing for y in terms of x. So in this case, notice we're not talking about z, so we're going to eliminate z. And to do that, I'm going to multiply equation 1 by 5 and equation 2 by 7. And here's what I end up with. Subtracting these two equations, I end up with -19x minus y is equal to 0. And here I end up with y is equal to -19x. What I have now is all my variables in terms of x. So therefore, vector n is x, and we go to the y, that's -19x, and the z is 11x. And if we want, we can factor out the x. So we're left with x bracket 1, -19, and 11. So this tells me that the normal to both a and b must be collinear to the vector 1, -19, and 11. And now I can choose any x value I want, and I can find any vector that's perpendicular to a and b based upon this equation. In this particular example, however, the cross product is the vector with an x value equal to -1. Which tells us that n is equal to, if we take our two vectors, a cross b, is equal to -1, 1, -19, and 11, which equals -1, 19, and -11. So this right here is our notation for the cross product. And for this particular example, the cross product is this particular vector. We're going to see why this is the vector that represents the cross product in a moment. So what is the cross product? So the cross product of two vectors a and b in 3 space is a vector that's perpendicular to both a and b. Keywords: perpendicular to both a and b, such that vectors A, B, and A cross B form a right-handed system. So that's why we ended up with the example above. Instead of being positive 1, it had to be negative 1 based upon a right-handed system. So in my diagram here, assuming that vector A is facing towards us and B is going away from us. And using the right-handed system, this tells us that A cross B is going to be the opposite of B cross A, which means that A cross B is equal to the negative of B cross A. So if I did B cross A, that would be this vector right here. This would be B cross A. It would be pointing in the opposite direction based upon a right-handed system. So I'm going to play a short video for you right now that tries to explain how to determine the direction of A cross B.
To determine the direction of the cross product for A cross B, you need to use your right hand and point your fingers in the direction of A. Then you need to curl your fingers toward vector B using angle theta, the smallest angle between vectors A and B, when the vectors are arranged tail to tail. With the correct orientation, your thumb will be perpendicular to vectors A and B, pointing in the direction of A cross B. Therefore, A cross B should be pointing into the page or out of the page. In this example, you will see that if you point your fingers in the direction of A and curl towards B, A cross B will be pointing into that page. If we try to find the direction of B cross A, when you point in the direction of vector B and curl your fingers towards vector A, your thumb will be pointing out of the page, and therefore B cross A will be in the same direction.
Normally we would develop the formula for the cross product, but just to save some time, I'm going to give you the formula, and then if you want to know more about it, let me know. So the formula for calculating the cross product of algebraic vectors, given A is A1, A2, A3, and B is B1, B2, B3, is given by the following formula. A cross B is equal to this formula right here. And notice it's split into 3 parts. There's your x component for your vector, there is your y component, and there is your z component. So let's try using this formula to determine the cross product for the 2 vectors we started with, A and B. So what we want to determine is A cross B, which means we're going to take vector -1, 4, and 7, and we're going to cross it with 2, 3, and 5. Just note that this would be A1, A2, A3. This is B1, B2, and B3. We can now determine the cross product. So first of all, it says A2 times B3. So that's going to be 4 times 5. So that's going to be 20. Minus A3B2. A3B2 is going to be 21. And then the formula says we have A3B1. So that's 7 times 2, which is 14, minus A1B3, which is -5. And then for the z component, A1B2, which is -3, minus A2B1, which is 8. You see that we end up with -1, +19, and -11, which recall we stated above this was the cross product of A cross B. So that's the same thing we had up here that we highlighted. Now this is one way of determining the cross product using the formula. I'm not a big fan of memorizing formulas, so another method of calculating A cross B is to use what I call an algorithm. The algorithm that I use starts by writing each vector 2 times. So I'm going to do A cross B. So A has components A1, A2, A3, and then I write them again, A1, A2, A3. For our second vector, I write them out twice as well, B1, B2, B3, B1, B2, B3. So I'm going to get rid of the first and last term that I have in this list. And then all I do is take the down product minus the up product. So I draw my arrows, and notice here is my x, if you like. So my x is equal to a2b3 minus a3b2. There's my x. And if I go back to the top, that's what it says there, a2b3 minus a3b2. So next, let's show with the y. If I take the y value, so the y value is going to be a3b1, the down product or the down arrow, minus the up arrow, a1b3. And then finally I can take these z values, and I get that z is equal to a1b2 minus a2b1. And normally you'll have numbers for this, so you won't be writing out all these letters, but now you can compare this to the formula above, and you see these are the same variables that we have here. So let's try this method. So we want the cross product for the following two vectors, a cross b. So that's -1, 4, and 7, and again we're crossing it with 2, 3, and 5. At the side I'm going to write out the components twice. So I have -1, 4, 7, -1, 4, and 7, and then I have 2, 3, and 5, 2, 3, and 5. I get rid of these two. And then the down product minus the up product is 20 minus 21. So that was this right here, 20 minus 21. And then 14, and that's going to be plus 5. So 14 minus -5 is plus 5. And then finally, -3 minus 8, -3 minus 8. And this gives me -1, 19, and -11. So again, you can use the formula, or you can use this algorithm. Last thing, now that we've shown you how to find a vector perpendicular to two other vectors, how could you verify that A cross B is perpendicular to both A and B? So recall that we can now take the dot product, so we can take A and dot it with A cross B, and if they are perpendicular, we should end up with the result of 0. So we're going to take -1, 4, and 7, and we're going to dot it with -1, 19, and -11. Same thing with B. I can do B dot A cross B, and for this we'll have 2, 3, and 5, and we'll dot it with -1, 19, and -11. So this is a good way to check your work. So -1 times -1 is 1. So 4 times 19 is 76, and 7 times -11 is -77. And you see we get 0. So this tells us that A cross B is perpendicular to A. And now we check the next vector. So 2 times -1, -2. 3 times 19 is 57. And 5 times -11 is -55. And again, we end up with 0. So A cross B is indeed perpendicular to both A and B, and A cross B is that one particular vector that satisfies the right-hand rule. Try the following questions, and good luck.